Hi guys, it's Miss Simon. So I wanted to do this video today in order to help you guys out with science. So remember, we finished up in science. We were talking about that last non-contact force of gravity. And we kind of had two main scientists that we talked about that had to do with gravity. We had first Aristotle, who said and observed really gravity, but he never did any experiments. And then you had Galileo, who actually went out and proved Aristotle wrong, that gravity had nothing to do with the weight of objects, because he dropped those balls off of the Leaning Tower of Pisa, and they were the same size, just different weights, and the one that they dropped at the same time. So before we get started, we're going to talk about one more scientist that has to do with gravity today, which is Sir Isaac Newton. I'm sure many of you have heard of him before, because Newton does have his 3 laws of motion, which we will talk about not today, but later on this week. But I just kind of wanted to review. I looked over you guys' practice quizzes, and most of you guys did a really good job with that. A lot of us I saw missed that last one that talked about the explaining the reason why a rock is going to hit the ground first instead of a feather. Okay, most of you all said that the rock was going to hit the ground first, but the reasoning that you said was wrong. So I want us to kind of go back and think about what we're talking about the other day. So when we have this rock and this feather, okay, yes, the rock is going to hit the ground first, but remember, the rock is hitting the ground first because the force of friction is acting more on the feather itself. So that air friction has more of an impact on lighter objects, okay? So the rock's not falling first because it's heavier, it's falling because of the air friction that's acting on the feather, okay? Just wanted to kind of clarify that one before we kept moving. All right, so I'm gonna share my screen with you guys with the presentation, and then I'll, like I've done before, I'll highlight what you guys kind of need to write down, and we'll discuss it as we go. Hold on, guys, let me see real quick. Okay. Now, hopefully I should be able to share it with you. Why it's not working? All right, let's try this one more time. There it is. Okay, so now you should see on your screen the presentation. So like I said the other day, like I just said, we're gonna talk about one more scientist that has to do with that non-contact force of gravity. And his name is Sir Isaac Newton. So go ahead and just continue on in those notes that you have on gravity. And go ahead and put your next note as Sir Isaac Newton. And like I said, many of you might have heard of him before because he does have his laws of gravity, which we will talk about. So in 1687, Sir Isaac Newton published Principia, which explained nearly everything that had to do with moving objects. And that's where he kind of got his ideas and his laws of motion from, as well as creating advanced mathematics to solve and predict the motion of objects. So basically what he did was he took Aristotle's and Galileo's ideas and he kept expanding on them. He added math to those ideas. So what you guys need to know about that is, as well as creating advanced mathematics to solve and predict the motion of objects. Okay, so not only did he come up with like laws and principles, he added mathematics to everything. So go ahead and add that in there. Okay, and then what else that you need to know about him is that his work expanded on gravity and kind of took Galileo's ideas and experiments and ran with them. So first we have Aristotle. Remember, he just observed. Then we got to Galileo, who took Aristotle's observations and started experimenting. And now you have Sir Isaac Newton, who took Galileo's experiments and expanded on them even more by adding mathematics and kind of theories to that as well. Okay, so make sure you have that in your notes as well. So there's kind of the three main scientists when we're talking about gravity. And this is just a picture of what Sir Isaac Newton looked like. All right, moving on. Ooh, too fast, sorry. All right, so his discovery. Many books report that while sitting outside after dinner with a friend, Newton saw an apple fall from a tree and hit the ground and then discovered gravity. So I'm sure many of you, when you were a kid, you said the reason gravity was discovered, you heard the story of an apple falling from a tree. Well, it might have been shocking for Newton, that's not quite true. Okay, so that whole story of the apple falling from the tree and then gravity was magically discovered isn't really true. People already knew about gravity way before Newton, and we learned that with both Aristotle and Galileo. People knew gravity was existing because they knew that if they had a marker and they dropped it, it's gonna fall, okay? And that explains gravity. It didn't take an apple falling from a tree for people to realize that. All right, so we're gonna look at these rules specifically of gravity. So what Newton did was to apply mathematics to the falling apple. So he explained why the apple fell in the direction that it fell. And proved why objects fall in a straight line, okay? So again, we can kind of look at this example of the marker. When I drop this marker, it falls straight, okay? It doesn't fall around in a circle, it doesn't spin all around before it falls, it just falls straight down. And apples don't fall off a tree and go in circles. They fall straight towards the center of the earth. So his equations also illustrated the strength of gravitational force. He used mathematics to explain the world around them, okay? So again, he made gravity mathematical. That was Newton's big thing. So you guys need to write down this rules of gravity. What Newton did was apply mathematics to the falling apple and prove why objects fall in a straight line. Apples don't fall off a tree and go in circles. They fall straight towards the center of the earth. Okay, so we can look at that. Go ahead and write that down. And also I want you to go ahead and draw this picture as well, because this picture really does a good job explaining it, okay? And we can think of this as more than just apples and markers, okay? Anything that drops is gonna fall straight down, okay? It's not falling in circles, it's falling straight. And that's what Newton set out to kind of prove with his mathematics. So I'll give you a second, go ahead and write that down. All right, so moving right along there. Okay, so this can also be explained by Earth's gravitational pull. So the gravitational forces on Earth pull any object near or on Earth's surface down towards the center of the Earth. So everything is always pulled down towards the center of the Earth. It doesn't matter what it is. According to gravity, everything's pulled down towards the center. Okay, and we can talk about that with any objects. If we look at this picture, all of these things are pulled down towards the center of the earth. Okay, we have dogs, we have planes, buildings, even you guys, and cars. Everything is pulled down. Okay, it doesn't spin around, it doesn't go upside down. Everything is pulled down to the center of the earth. So go ahead and add this to your notes. No way. Make sure you put Earth's gravitational pull, and then you can add this stuff as well. The gravitational force on Earth pulls objects near or down towards the Earth's center. That's very important, okay? And that's pretty much common sense, just like we just talked about. Everything is being pulled down. It's not being pulled up, it's not going sideways, left or right, it's just down towards the center of the Earth. I'll give you a minute to write that down. Okay, and feel free to draw this picture if it helps you, okay? All right, moving on. Okay. So now we're going to kind of talk about what I said we would get back to earlier in the unit, why the moon doesn't crash into the Earth, okay? And that's going to be explained in this as well. So Earth's gravitational reach. Newton's discoveries went one tremendous step beyond apples, okay? He made the bold statement that the same gravitational force that attracted the apple to the Earth also attracted the moon to the Earth, okay? But now we go back to that question we asked earlier in the unit. The apple falls down and hits the Earth, but the moon goes around it. Well, why is that? And that's what we're going to kind of look at today. So Newton was able to not just describe apples, but he was able to describe the moon and the Earth. And we're going to talk about why the moon does not crash into the Earth. The truth is that the moon is constantly falling towards the center of the Earth, but the moon is moving so fast in a direction that is perpendicular to the Earth that it moves in an ellipse around the Earth. Okay, so I'm going to kind of explain what that means. So what we just learned is the moon is constantly, if you look at this picture, the moon is constantly falling towards Earth because gravity of the Earth is pulling the moon in. It wants it to fall down to the center of the Earth like everything else. So the Earth is pulling on the moon and the moon is constantly falling. But the moon is not just falling in this direction, it's also going in an orbit around the Earth. So you kind of have an L shape going on, and that's kind of what we learn in math with the words perpendicular. You have angles that form a right angle. Two lines that form a right angle shows that perpendicular motion. So when we look at this, this is being pulled this way, and the moon's also being pulled this way, okay? So the combination of it being pulled this way and it being pulled this way allows the moon to not fall into the Earth. So the combined effects of the moon's own gravitational pull and its perpendicular velocity keep the moon in orbit around the Earth. So because of that perpendicular motion, because of those two things working together, that's why the moon does not fall into the Earth, okay? So it is a delicate balance. It's a balance between both the Earth pulling on the moon and the moon orbiting the Earth. So it makes that perpendicular relationship. Okay, so I'm going to tell you this one you guys do kind of have to write down and draw the picture on. So delicate balance. The moon is constantly falling, sorry, towards the center of the Earth. The Earth is moving so fast that it moves in an ellipse around the Earth. Okay, so go ahead and write that down. Also, I do want you to draw this picture. Please make sure you have the moon, the Earth, and that we see the gravity's pulling it this way, and that the moon is going this way in its ellipse around the Earth. Okay, and then also after you get that down, go ahead and put the combined effects of the moon's pull and the perpendicular motion allows the moon to orbit the Earth and not fall into the Earth. Okay, so the moon, again, is constantly falling towards the Earth, but because of that balance between the pull of the Earth's gravity and that orbit around the Earth, it makes that perpendicular so it doesn't crash it. All right, moving on. If you're not done, you feel free to pause the video and then hit play when you are finished. Okay. So, and you can simulate this orbit. So what simulate means is you can kind of copy it. You can show why it works. So you can simulate this motion by swinging a ball attached to a rope above your head. You're pulling in on the ball like gravity, but it is moving so fast that it goes in a circle. You're acting as Earth. The rope is standing in for gravitational force, and the ball is like the moon, okay? So what happens basically, guys, is if you were to swing, and I'm sure many of you have, like if you've played ball or something before and you've had a ball that's attached to a rope, you can swing it above your head. And when you're swinging that above your head, you notice that it doesn't fall on your head, okay? And so that ball can represent the moon, all right? So if you are swinging it above your head, you can represent Earth, okay? And that swinging represents the motion of the moon, okay? We notice that the ball is not going to hit you in your head as long as you keep swinging. But what happens when you stop swinging, okay? When you stop swinging, the ball is going to fall, okay? It's going to hit you in the head, or it's going to fall to the center of the earth, okay? Because that swinging is what keeps it from falling, okay? And that's quite similar to what keeps the moon from falling into Earth. That orbit of the moon around Earth, that orbit of it constantly moving, keeps it from falling and hitting Earth. And we can kind of see that in that picture here, okay? So in this picture, he's swinging that ball above his head, okay? And it's staying above his head. Then we see here, oh, the string breaks, so that ball is going to fall. Okay, now I want you guys to think of that question. What happens when what happens to the ball when the gravity is not present? What happens when that string breaks? Okay, and obviously you're gonna see that what happens when that string breaks is the ball falls, okay? So the reason the moon does not fall into the earth is because of that balance of Earth's pull and the orbit of the moon around the earth. Okay, to kind of help you, you don't really have to write anything on this slide down, but I would draw this picture of the man swinging the ball above his head, because that would kind of help you guys visualize it in a different way too. All right, so let's go through some of these questions, make sure we understand what we learned today. So who explained gravity using special mathematical language? Okay, either Aristotle, Galileo, Newton, or Plato. Well, Plato we have not even learned about yet. So it would have to be Newton. Remember, Newton applied that mathematics to it, okay? So Aristotle was just observation, then Galileo actually experimented, but Newton was the person who added specific mathematical language. So you should have gotten Newton for that one. All right, let's see what the next one is. In which direction does Earth's gravitational force pull objects? Up and away, opposite of Earth's rotation, down towards the center of the Earth, or in the direction of the Earth's rotation? Okay, in which direction does Earth's gravity pull objects? Okay, you should have chose C, down towards the center of the Earth. That's what we just learned. The Earth is constantly trying to pull everything down towards the center of it, down to that Earth's core. Okay. All right, so this is a lab that you guys are going to perform on Wednesday, okay? And I'll do a quick video on Wednesday to kind of explain what that's going to be. And you can use objects. You're going to be able to do it just with objects that you find all around your house, and you're going to see why this idea works. So let me stop sharing the screen with you. Okay, so I hope that presentation was helpful. Make sure everything that I highlighted you kind of have down in your notes, okay? And I'll see you guys soon. Bye.